Welcome to this installment of Epidemiology of Everyday Life Lessons. In this video, I will describe how we can use the Gaussian distribution, which you might know better as the normal distribution, to solve a simple example problem. Let's recall that in our model, we have our estimate, the best guess of the data. For a simple model that we've been using, the value is the mean, which we represent with the symbol y bar. We represent the uncertainty of the model with the standard deviation, which we represent with the symbol sigma. The mean is our best guess, and the standard deviation tells us how good that guess is likely to be for any given observation in the data. For continuous variables, we use a histogram to describe our data. For this example, we will use the height of women from the National Health Interview Survey. On the x-axis, we write out values in equal intervals. In this case, it's very easy. Each interval equals 1 inch in height. On the y-axis, we count the number of observations that fall within that interval. So in these data, 368 women are taller than 58 inches, but shorter than 60 inches. 797 women are taller than 59 inches, but shorter than 61. That means that just over twice as many women fall in the second category as compared to the first. So the bar is just over twice as tall. Next, 906 women are taller than 61, but less than 62 inches tall. Only about 100 more women are in this category compared to the former, so the bar reaches only a little bit higher. Then we go on for the rest of the categories in the data here. Now let's get to a problem. Let's say that we own an amusement park and we want to design a piece of equipment, maybe a safety harness. We want to design the harness to fit women up to the 95th percentile of height. To do that, we can figure out where the 95th percentile of observations fall. The NHIS data have 13,629 women. 13,629 times 0.95 equals 12,947.55. So, since we can't have part of a person, we round up, making the 12,948th woman represent the 95th percentile. As we go through our histogram, we can count the number of women in bins until we get to that number, 12,948. At 59 inches, as we said before, we have included 368 of the women in the data. At 60 inches, we have included 1,165 of the women. At 61 inches, we have included 2,071. At 62 inches, we've included 3,842. And we keep going like this until we get close to the number that we want. And at 66 inches, we are getting close. 11,042 women are 62 inches or shorter. At 67 inches, we include 12,247 of the women in the data. And at 68 inches, we have gone over the 95th percentile, but just barely. 13,003 is only 55 women more than our target of 12,948. So the value is less than 68 inches, but just barely. So we can conclude that our answer is almost 68 inches. One thing that we could have done was to sort our data to find the height of the 12,948th woman in the data. But that requires including all 13,629 pieces of information. The histogram, on the other hand, summarizes our data for us. We have turned those 13,629 pieces of data into 12, the height of each bar. But it's possible to reduce the amount of information that we need even further than these 12 pieces of information. To do that, we will use this. This monstrosity probably scares well, this is a family-friendly video. Not only that, I said that we would simplify things, and this seems to make things a lot more complicated. But you probably recognize this thing in a different form. A bell curve. The curve on the right, which you have probably seen before, follows the equation on the left, which you have probably not seen before. The formula represents a model for data that follow a Gaussian distribution, which we also refer to as a normal distribution. When we look at our data, we see that the normal distribution approximates the distribution of heights among women pretty well. And remember that we are modeling the distribution, which means that we trade off some error for greater simplicity. And since it fits our data pretty well, we're willing to use it. So now let's try to answer the same question that we did before, but using this Gaussian distribution rather than the histogram, what we also call an empirical distribution. We want to do the same thing that we did before. find 95% of the area under the curve. But instead of calculating that area based on the count of observations in the histogram, we will use the functional form to do the counting for us. The first thing that we do is convert our units to standard deviations rather than inches. When we write the units in standard deviations, the sum of the entire area under the curve equals 1. That is where the standard in standard deviation comes from. This is called the probability distribution function. It turns out that 1.64 standard deviations above the mean gives us 95% of the area under the curve. That means that the integral from negative infinity to positive 1.64 equals 0.95. But fortunately for you, we won't be solving integrals. Another way that we can say that 1.64 is the answer that we want is to say that it's the z-score that covers 95% of the distribution. You might have had the experience of looking at values on the z-score table and possibly nightmares about it too. But we won't be doing that either. Instead, we will use R. For this, we will use the Q-norm function. This gives us the z-score for the 95th percentile. And we see that the value rounds to 1.64. Now let's recall that the area to the left of 1.64 standard deviation covers 95% of the distribution. Now we want to convert that to inches. First, we substitute the standard deviation for the distribution into the equation. The standard deviation for the data equals 2.54 inches. We multiply that value by 1.64 standard deviations. We end up with a value of 4.17 inches. That means we capture 95% of the distribution when we reach 4.17 inches above the mean. We can substitute the actual value of the mean, which is 64.14 inches. And we end up with a value of 68.30 inches as our estimated value that captures the heights of 95% of women. To summarize what we just did, we can use a formula. Y star, the value we want to estimate, in this case where 95% of the distribution falls, equals Y bar, the mean, plus the z-score for the critical value times sigma, the standard deviation of the data. Plugging in the numbers from our data, we have, and we can confirm that our units cancel correctly and we get our answer. Now that 68.30 inches is pretty darn close to the value that we guessed from our histogram. But now we use only two pieces of information, the mean and the standard deviation, rather than the 12 that we used for our histogram, or the more than 13,000 that we used if we wanted to sort the data empirically. We have just simplified the world in a useful way. So the Gaussian distribution provides us with a model to summarize all of the data, even if we have millions of observations using only two numbers, the mean and the standard deviation. So that concludes this epidemiology of everyday life lesson. In future videos, I will describe how we can use the information to make useful predictions about the world. Thank you for joining me, and I hope to see you for future episodes.